Today we will be talking about the second derivative test. So in the previous video we already did the first derivative test and we saw that the first derivative test helps us find the maximum and minimum and helps us find when is the function increasing or decreasing. Now what does the second derivative test helps us with? It helps us see how our graph will bend and tell us whether our critical point is a maximum or a minimum. So it is an additional step to the first step that we had, which is the first derivative test. And the second derivative test is used to find the concavity, where we have two options, either concave up, which is denoted as a U, or a concave down, which is U flipped. And it helps us find the point of inflection. Let's go straight to an example to make it more clear. First, we'll be given our function f of x. To be able to solve the second derivative test, first we'll need to find the first derivative, which is f prime of x. We derive it. The derivative of x cubed is 3x squared, and the derivative of negative 3x is negative 3. And we equate it to 0. Now to solve for x, we take the negative 3 to that side, where we'll have 3x squared equal to 3. We divide by 3, so that we can keep the x squared by itself. And now we'll have x squared equal to 1, which means x squared minus 1 is 0, which means x minus 1, x plus 1 is 0. So x is either 1 and x is either negative 1. And now we used to do the table for the f prime or the first derivative test. Here I won't waste much time. There'll be another video to explain it further and do the full steps all together and draw the graph as well. Now, as we are talking, we care about the second derivative test to find the concavity. So second derivative test means we do another derivative for the derivative. So we derive now the 3x squared minus 3 equal to 0. Derivative of 3x squared is 6x, and the derivative of negative 3 is 0. So we'll have 6x equal to 0. Divide by 6. So x is 0. Now we do our table like we did in the first derivative test, where we have x, f double prime, and f. And of course our domain is from negative infinity to infinity, since we don't have any restrictions or conditions. And the same thing we used to do in the first derivative test, we put a line in the middle and we put a 0 on it and a 0, which means f double prime at 0 is 0. Now we take test values, number between negative and infinity and 0, let's take negative 1, and the number between 0 and infinity, which is 1. And now we replace it into f double prime. So f double prime at negative 1 is 6 into negative 1, which is negative 6. And what we care about here is the sign of the number that we get. So here the sign is negative, and that's what we care about. So we put here a negative. We do the same thing for f double prime at 1. So 6 into 1, which is 6. 6 is a positive value, so we put a plus sign between 0 and infinity. Now, as we mentioned here, concave up, we put a u, and concave down, we put a u flipped. Concave up means whenever our function gives a positive value. Concave down is whenever we have a negative value. So here we have a negative between negative infinity and 0, which means our function will be concave down. And we have a positive between 0 and infinity, which means our function will be concave up. And now we can write f is concave up on an interval from 0 to infinity, and f is concave down from negative infinity to 0. Now, as we had a maximum and minimum in the first derivative test, here we have something called a point of inflection. The point of inflection here is whenever f double prime equal to 0, which is in our case at 0. So we have point of inflection at x equal to 0. And now to find the y value for it, we need to replace into f of x a 0 instead of x. So we'll have 0 cubed minus 3 into 0, which is 0. So our point of inflection is 0, 0. That's the first example. Let's do another one as well, just to make sure that you understand it fully. Let's say we have f of x is x cubed minus 6x squared plus 9x. First things first, we apply the first derivative for f of x. So we'll have f prime of x equal to 3x squared minus 6 multiplied by 2 is 12, x plus 9, and we equate it equal to 0. Now we need to factorize. And to factorize, we can take a 3 as a common factor here. We'll be left with x squared minus 4x plus 3 equal to 0. And now we can use mode 5-3 on the calculator, which will give us x minus 1, x minus 3 equal to 0, which will give us x equal to 1 and x equal to 3. Now, these are for the first derivative test. Let us just highlight them, and I'll tell you their importance at the end. Now we need to solve for f double prime of x. F double prime of x is the derivative of the f prime of x. We will have 3 times 2, which is 6, x minus 12 equal to 0. And now we need to solve for x. We take the negative 12 to the other side. We'll have 6x equal to 12. We divide by 6. And we'll have x equal to 2. And since we have no conditions here, our domain is from negative infinity to infinity. Now, do the same table that we did before. X, f double prime, and f negative infinity to infinity. And here, our special number is 2. So we'll have a 2 here, and we put a 0. Why? Because f double prime at 2 is 0. Now, we take test values, a number between negative infinity and 2, for instance 0, and a number between 2 and infinity, for example 3. And now we replace them in f double prime. So f double prime at 0 is 6 into 0 minus 12, which is negative 12. Negative 12, and we care about the sign of it. So it's negative. Negative means concave down. Now, f double prime at 3, we have 6 into 3 minus 12, which is equal to 18 minus 12, which is equal to 6. 6 is a positive number, so it's positive here, concave up. Now we write f is concave down from the interval negative infinity to 2, and f is concave up from 2 to infinity. And now we have a point of inflection, which is at 2. Point of inflection at x equal to 2. Now we'll need to find the y value for it. To find the y value, replace f at 2, which means we'll have 2 cubed minus 6 into 2 squared plus 9 into 2. 2 cubed is 8 minus 6 multiplied by 4 plus 18, which means we'll have 8 minus 24 plus 18, which will give us 2. So our point of inflection will be at 2, 2. Now, I'll explain something that I didn't explain in the previous example. We said we had as maximums and minimums 1 and 3. So we don't know what they are. So let's put 1 and 3. And we have our point 2. Before our point 2, we're looking here now. Before our point 2, we had a sad face, which means our function was going like this. And after it, after point 2, our function went up, which means our 2 is here, our 1 is here, and our 3 is here. Why is that important? Whenever we have a concave down, it creates for us a maximum value before it, or in the interval where we have a concave down, and whenever we have a concave up, we'll have a minimum value in the interval where it is concave